Sodium-ion is getting attention right now, and it is important to understand that sodium-ion batteries are not a magic trick. They are a close cousin of lithium-ion. The basic idea is the same. Ions move back and forth between an anode and a cathode. That movement stores energy and then releases it. The big difference is the ion itself. Sodium ions are larger than lithium ions. That sounds small, but it drives many trade-offs. The reason people care is cost. Sodium is abundant and easy to source in many regions. That can reduce supply risk. It can also cut raw material costs. Many sodium-ion designs can use materials that are easier on the supply chain than nickel or cobalt-heavy chemistries. Safety is another selling point. Several sodium-ion chemistries are less eager to run away under abuse, and there is a practical bonus that keeps showing up in tests. They can operate well at low temperatures. That matters for vehicles that must start in deep cold, and for grid packs that would otherwise need tight thermal control. Even so, none of this matters if the final cells are not competitive on the factory floor. A battery is not judged by a lab sample, it is judged by price per kilowatt hour, by yield, by how hard it is to build, and by how stable the supply chain is. That is why I went looking for the missing detail that could move sodium-ion from promising to scaling. The real problems people point to, once you read past the headlines, the doubts are not hard to find. The first is energy density. Because sodium ions are larger, cells often store less energy per kilogram than lithium. That matters most for cars. The second issue is efficiency. Higher internal resistance means more losses. Losses become heat. Heat forces you to limit power or add cooling. Efficiency is also money. If you waste energy on every cycle, you need more generation to get the same useful work. The third issue is voltage behavior. With lithium iron phosphate, the budget lithium chemistry today, the voltage stays fairly flat as the cell discharges. That makes life easier for inverters, motor drives, and battery management systems. Many sodium-ion cells do not behave like that. In tests, the cell voltage dropped a lot as the state of charge fell. That hurts two ways. The electronics must handle a wider range, and constant power demand forces higher current as voltage drops because power equals voltage times current. Higher current means more heat, more loss, and often more expensive components. So the critique becomes clear. Sodium ion can be less energy dense, less efficient, and harder to manage electrically. That is why cost has to be the killer feature, or sodium ion stays a niche. Manufacturing and cathode innovation are, honestly, at the heart of what makes battery technology tick. It's not just about finding new materials, but about figuring out how to actually build these things efficiently and reliably on a massive scale. The way we make batteries, especially when it comes to the cathode, can totally change the game for cost, performance, and even safety. So, let's dig into why this matters so much. Why cheap materials still do not mean cheap cells is the part that confuses most people. If sodium is cheap, why were sodium-ion cells not already cheaper than lithium iron phosphate? A big reason is manufacturing. Raw materials are only one slice of cost. Factories, solvents, drying, yield loss, safety controls, and quality testing can dominate. If your process is messy or fragile, the scrap rate eats your savings. I found a study from Stanford that laid this out in a sobering way. Someone from the limiting factor channel also used it in a strong analysis. The paper showed that even with cheaper feedstocks, sodium-ion cell costs were still on average higher than lithium iron phosphate at the time of the study. It also suggested that cost par might take longer than many forecasts claim. That sounded like a cold shower, but it also made the search more focused. If the chemistry is cheap but the cells are not, the lever is the process. Something in the cell design must unlock a simpler, cheaper manufacturing route. That is where the cathode matters. The cathode is not just an energy store. It shapes voltage, efficiency, and power. It also dictates what binders and solvents you must use, how sensitive the powder is to air or moisture, and how much work it takes to make a clean electrode. So, instead of asking, is sodium cheaper than lithium? The better question became, can sodium ion be built with the same kind of low-cost, high-yield process that lithium iron phosphate already enjoys? Now, first, like always, be sure to hit the like button down below. It helps us out tremendously with the reach of this video. Thank you. The first path in the Prussian white trade-off is where we see a company like this not start from nowhere. Their early sodium-ion packs leaned on a cathode family often called Prussian white. One reason is the discharge curve. Prussian white can give a flatter voltage profile than many layered oxide designs. So, the electronics problem is smaller. Another reason is manufacturing fit. Prussian white electrodes can be made with water-based slurry processes that look a lot like the ones used for lithium iron phosphate. That matters because this company already has massive lithium iron phosphate production lines. Prussian white also reached a respectable energy density around 160 watt-hours per kilogram in announcements and reports. For stationary storage, that is often fine, but there is a ceiling. If sodium-ion is going to scale fast, it needs access to the electric vehicle market because EVs drive most battery volume. If sodium-ion cannot win a place in vehicles, it struggles to hit the same learning curve that lithium enjoyed. From that angle, Prussian white looks like a bridge. It proves the concept, but it may not be the final answer for mass adoption. To compete in more vehicle segments, you need higher energy density. That points to layered oxides, and that is where the old manufacturing pain began. The reinforced cathode that changes the economics is the next piece. Layered oxide cathodes can offer higher energy density for sodium-ion. That is why they keep coming up in second-generation plans, but they have two painful drawbacks. First, many show the steep voltage drop during discharge, which makes system design harder. Second, they have been harder and more expensive to manufacture at scale. Traditional approaches often rely on special organic solvents that are costly and can be toxic. Those solvents add handling costs, slow down production, and make it harder to run a simple water-based electrode line. Here is where a specific patent matters. The patent describes adding antimony, shown as SB, to reinforce a layered oxide cathode. The key claim is water resistance. So, let's talk about the future of energy storage. Things are moving fast, and honestly, the next wave might come from some unexpected places. Technologies that were once considered niche are now getting real attention, especially as costs drop and performance improves. It's not just about squeezing out a little more efficiency, it's about changing the game entirely. The choices we make now, in terms of chemistry and manufacturing, could shape how we power everything from cars to cities for decades to come. As we look forward, the question is not just what works in the lab, but what can scale up and make a difference in the real world. With the additive, the cathode material can survive contact with water without breaking down. That sounds like a chemistry footnote, but it is a manufacturing unlock. If the cathode is water-resistant, you can use the cheaper water-based slurry process that this company already masters. You can run faster lines, reduce solvent recovery systems, and avoid a chunk of safety costs. The patent even shows simple evidence. In an X-ray diffraction comparison, a standard layered oxide sample changes a lot after water exposure with peaks fading or shifting. The reinforced sample shows far less change before and after immersion. You do not need to be an XRD expert to read the message. One material degrades, the other holds its structure. That is close enough to lithium iron phosphate for many vehicles, especially where low cost matters more than maximum range. There is also hope for better voltage behavior. Some literature suggests the antimony reinforcement can flatten the discharge curve and lift the average voltage compared to older layered oxide sodium cells. If that holds up, the current rises smaller, the heat is lower, and the power electronics can be simpler. This company is not betting on one tweak either. They have discussed self-forming anodes and other methods to push density higher. But the reinforced cathode is the key economic lever because it attacks the manufacturing bottleneck directly. If sodium-ion enters starter batteries, trucks, and budget EVs, volume ramps and costs fall. That loops back to the Stanford cost curve. If prices move toward prices below about $25 per kilowatt-hour, grid storage and cheap EVs scale much faster. Lithium will not disappear, but sodium-ion may become the go-to option wherever price and robustness win. And that shift will be huge for everyone. Cheap batteries change everything. If sodium-ion can reliably undercut lithium iron phosphate, whole markets open up. Trucks can start in deep cold. Entry-level EVs can get a decent range without premium packs. Grid storage can grow without fighting for lithium supply. The reinforced cathode with its antimony-stabilized layered oxide looks like a practical route to scale because it fits water-based manufacturing. That does not mean sodium-ion wins overnight. Energy density, efficiency, and voltage behavior still matter, but it does suggest a tipping point. The next few years will show how fast this curve drops and what it means for us.